Okay, so today we will talk about some elementary number theory. So number theory really concerns properties of the set of integers. So let us denote that set by z. So this is the set of integers. So recall this just all numbers 0, 1, 2, 3 and so on. Also the negative integers. And so sometimes we will just restrict ourselves to the positive integers, it's not too important. So the key property of integers that one studies, or the very first property, is the notion of divisibility. So let us just define this formally. So given two integers n and d, so given let us call it n and d integers, we say that d divides n. So we say that there are several different equivalent ways of saying this. So we say that let us call it n is divisible by d, okay, if n is some multiple of d, if n can be written as qd for some integer q, for some integer q. Okay. So there are other ways in which we express this. We also say that if this happens, we often say d divides n, or that n is a multiple of d. Okay. So they are all just other ways of expressing the same thing. So let me just say also another common thing, commonly used expression is that d divides n. And this of course has a notation which is very convenient in many situations. So this is the notation. We write d divides n, divides just being this vertical line over here. So that is the notation for divisibility. So what are examples? Of course this is very familiar and easy. So for instance 3 divides 6, because 6 can be written as 3 times 2. 13 divides 52, because 52 is 13 times 4 and so on, etc. So you can think of a large number of such examples. It is also interesting to keep in mind that these numbers could be negative here. For instance, we would say that 3 divides minus 6. Similarly, minus 3 also divides 6, for instance, because minus 6 can be written as 3 times minus 2. And similarly 6 here can be written as minus 3 times a minus 2. Okay. So these are also perfectly valid ways of they are also they also fit the definition of divisibility. Now here's here are some border cases which we need to keep in mind. D, no matter what d you pick, always divides 0. Okay. So d divides 0 for every d, for every d in z, because 0 can always be written as d times 0, right. So 0 is a multiple of every number. Similarly 1 divides every number n. So 1 divides n for every n in z. Okay. So every number is a multiple of 1. Similarly, because n can be written as 1 times n. Okay. So these are some sort of the, as I said, the borderline cases to keep in mind. Now of course we do not always have divisibility, meaning every number does not divide every other number. So a useful thing to keep in mind is the notion of division with remainder. So I should call it division with remainder. So what does this mean? Well, let us write it out formally first and then we will write out examples. Let n and d be integers, and let us assume that d is positive. It is just an assumption for convenience. So if d is positive, then there exist unique integers, then there exist unique let's call them Q and R, the quotient and the remainder, such that n can be written as Q times D plus R, and the constraint on R, the remainder, is that it's a number between 0 and D minus 1. Okay, so R is greater than or equal to 0 and less than D. So that's the condition. And recall, this of course very much resembles the notion of long division of polynomials that we talked about at the very end. In fact, these are really, you can think of them as being two instances of the same principle. Okay, so this again is the formal statement, but I am sure the various examples are, I am sure you have seen this in examples. So here are a few of them. So if I take the number 52 for instance, that is n, and we try to divide it by 10, that is the d. So here is n and here is d. So of course it is not exactly divisible, but you can think of the quotient as being 5, so that accounts for a 50 and a remainder of 2. So that is the remainder here, that is R, and the quotient is a 5. Okay. Similarly, if I take it's 252 divided by, let us say, 13, so I have the number 52, I try to divide it by the number 13, and in this case it divides exactly. So it is 4 times 13 plus no remainder. So think of remainder now as being 0. So here the remainder is R is 0, quotient is 4. So an alternate equivalent way of defining divisibility, so you would say that D divides n if and only if the remainder is 0. Okay, so that's an equivalent way of stating the same thing. And here again, negative numbers need to be treated a little more carefully. So if for instance you try to divide the number minus 52, so if that is your number n, so now for convenience we have already assumed that D is positive, so let me say I try to divide it by the number 10, so that is my D. So of course you could still think of it as sort of being like, forgetting the minus sign for now, it is like dividing 52 by 10. So if you think of, say, the quotient as being minus 5 in this case, okay, so there is a minus 5, and if you see what is left, there is a minus 2 left. Okay, so minus 52 is minus 5 times 10 plus a minus 2. So you could be tempted to think of the quotient as minus 5 and the remainder as minus 2, but that is not okay, because we have, at least in the way we stated it, we have required the remainder to be a number between 0 and D minus 1. Okay, so the remainder has to be a number between 0 and 9, minus 2 is not allowed as a possibility. Okay, so this is not quite going to serve our purpose. Instead what we need to do is the following: we need to do something to get the remainder to be a positive number. So we increase, or well rather decrease, the quotient. Okay, you change the quotient by 1 so as to obtain a positive remainder. So here is an alternate way of writing the same thing. You can think of it as minus 6 times 10, so that is minus 60 plus an 8. Okay, that is still a minus 52, and now this is really the expression you want. So you should think of the quotient as being minus 6 and the remainder as being 8. Okay, so the remainder now of course satisfies the constraint that we wanted to satisfy. Okay, so that is about divisibility and division with remainder. So very important class of numbers are what are called the prime numbers. So what are the prime numbers? Well, an integer greater than 1, so this is what you would call a natural number. So before we talk about prime numbers, let us recall the set of natural numbers n is just, well, all the positive integers. So this is just 1, 2, 3, 4 and so on is what is called the set of natural numbers. So a prime number is a natural number, so a natural number p is said to be prime if the following, if firstly p has to be at least 2, so p strictly greater than 1, and further the only natural numbers that divide p are 1 and p, and the only natural numbers okay, so it has no other divisors other than 1 and itself. Okay. So again I assume this must be familiar. So what are the list of prime numbers? Well, at least we can write out the first few. So we have 2, 3, 5, 7, 11, 13, 17, 19, that is the full list of prime numbers until 20, but then the list really goes on. Okay. So it is well, there are in fact infinitely many prime numbers. We will come back to that in a minute. So here are sort of two different ways of thinking about prime numbers. On the one hand, they do not really have divisors other than 1 and itself. In other words, you can't really break them down. You cannot break them down into smaller numbers. So you should think of so here's a picture of prime numbers that it's useful to keep in mind. If they did have factors, so any number which has a divisor can be written as product of smaller numbers, but since prime numbers don't have divisors other than 1 and itself, you can't really break them down any further and write them as a product of smaller numbers. So that's one aspect of prime numbers, but there's sort of also a complementary aspect which is that every number can always be written as a product of primes. Okay, so this is another property, if you wish, of primes, that every number can be broken down into primes. Or every natural number can be broken down into a product of primes. Okay, so examples of the latter principle, if you have the number 60, so this is 2 into 2 into 3 into 5. Similarly, 630 for instance would be 2 times 3 times 3, 5 times 7, and so on. Okay, so this is often what we call the prime factorization, that an arbitrary number can always be written as a product of primes, and further this expression really is unique. Okay, so that's another important property of prime factorization. So every number can be broken down into primes, but in an essentially unique fashion. Okay, so further uniquely is another important and interesting feature of this. Okay, so for instance the number 630, if you wanted to write it down as a product of primes, the only sort of different looking expressions you can produce are things in which the primes are written in different orders. So you could probably want to write 630 as maybe 7 times 5 times 3 times 3 times 2, maybe in descending order of primes or in some other arbitrary order. But other than that, there isn't much you can do. You can't find another expression for 630 which say does not involve these primes, say for instance something which contains 13 as one of its factors. Okay, so such things are not possible. It's essentially unique, these expressions. Okay, so up to reordering. Okay, so let's come back to this property that I just mentioned, that it is an infinite list. So the list of prime numbers is infinite, is a very famous statement which goes back all the way to Euclid. So theorem due to Euclid says that there are infinitely many primes okay, and the proof itself is rather interesting and illuminating. It proceeds through contradiction. So let me just quickly sketch the proof, Euclid's first proof of this fact that there are infinitely many primes. So it says the following: suppose not. In other words, there are only finitely many primes. So let's give them names. So let P1, P2, PD, let's say, be the full list of primes. Okay, so you imagine for the moment that the list is finite and that's the full list. And now what you do is the following: you create a number. So you form the following number. Let n denote the product of all these primes, P1, P2, PD, but with 1 added to it. Okay, so you look at the number P1, P2, PD plus 1. So that's some natural number which is, well, bigger than all the primes, because it's in fact it's bigger even than their product. And now we do the following: n of course is some natural number, and sort of by using the principle that every natural number has a prime factorization. Okay, so let's write n. So here's the, let's break n down into primes. So here's the prime factorization of n. So we write n as, let's say, capital P1, capital P2 till let's call it capital Pk, where all the PI's are all primes. So they could of course be, there could be repetitions when you write down prime factorizations, as we just saw when we talked about 630 and 60 and so on. Some of these could be repeating. So that doesn't quite matter for us. So let's write n in this fashion, and let's do the following. Let's think of this as, well, two parts. The first P1, let's isolate P1, and let's think of the remaining as being another number, P2, P3 till Pk. Let's call that as Q. Okay, so this part is Q, the second number, and P1, remember, is the very first factor in this expression, is a prime, right? So P1 after all is a prime, it occurs in the prime factorization. So P1 being prime must occur in the list of primes, must occur in the full list of primes that we wrote out, must occur in the list of primes. In other words, it's some Pi. Okay, in other words, P1 has to be somewhere in the list. Let's call it Pi for some I between 1 and d. So for some I between 1 and d. So let's call P1 as the prime Pi. So here's what we conclude, that this number n is in fact of the form Pi times Q. In other words, it's a multiple of that prime Pi. Now on the other hand, n, we knew what n was. It is P1, P2, PD. So remember, in this list Pi also appears. So this is Pi will occur somewhere in the middle, plus a 1. So here are two different expressions for the same number n, but they are mutually contradictory. Okay, so these two expressions can't both be true at the same time. And why is that? Well, to see it, what we'll do is we'll move all these terms over to the left hand side. Okay, so this equality provides us the following equivalent reformulation: Pi times, so I'll keep the Q as it is, and I will subtract, I'll move this term over to the left. So and I'm pulling out a Pi common. So this is now P1, P2, PD, but in which Pi is missing. Okay, so Pi has now been pulled out. So this Pi term here, I'll put a hat on top to say that you should think of that term as being missing from this expression. So it's Pi times Q minus the product of the other Pi's is the number 1. Okay, so that's the conclusion we make finally. But observe, that's clearly not possible, okay, because the left hand side is a multiple of the prime Pi. It's Pi times some number, whereas the right hand side is a number 1. Okay, and a prime of course is a number which is 2 or more. So there's no way that a number that's bigger than 2 can multiply something out to give you the number 1. Okay, so this final expression here is a contradiction. and that in fact proves that our initial assumption was wrong, that the list of primes is finite. Okay. So that is really Euclid's rather ingenious proof that the number of primes is in fact is infinite, and since then of course there have been several different proofs using several different ideas. Okay. So next time we will talk about a little bit more that one can do with division with remainder and primes and so on.